So in that last video, we introduced quick union. So we had these up trees, and whenever we were trying to merge them, or find anything with them, we always went to the root. Unioning was going to the root and then changing some pointers. We ran into that degenerate tree case, as you could pretty easily come up with a bunch of series of unions that would kind of result in this degenerate tree, which kind of results in our kind of third implementation, and the last one we're really going to talk about today, which is this weighted quick union. So just being a little bit smarter about which one you make the child of which. So our goal is we are always going to pick the smaller tree to go under the larger tree. Because if we already have a large tree, and we're unioning on a small tree, well, if we make the small tree go under the large tree, kind of just underneath the root, it's not going to increase the height at all. But if we did the opposite, we tacked on a large tree underneath the small tree, it's going to increase the height of that. The idea is always put the small tree kind of under. So the way we're going to implement this is we're going to store the weight of each of these up trees. The weight is going to be the number of elements underneath its root. And we're going to have some kind of constant time lookup instead of having to traverse the entire tree to count it up. So we're just going to have some kind of count associated to each one. So now our union is going to be find the root of A, find the root of B, and then put the lighter root, the one with fewer nodes, underneath the heavier root. The idea being, if we're going to do union A, B, C, D, kind of before we kind of ran into this, if we always just make the second one the parent, we ran into this kind of worst case A, B, C. But now we're going to kind of always guarantee that we put the lighter one underneath. And so we're going to end up with kind of this nice structure A, B, C. Now, how did we end up going about that? Well, we could draw out kind of the individual steps. We start by unioning A and B. So there's a tie. They both have the same weight. So maybe I'll make A point to B. And now I want to, colors here. Now I want to do union B and C. So I find the root of B. I find the root of C. Now I'm going to put the lighter one underneath the heavier one. So since C has fewer nodes, I'm going to put it underneath. I'm going to make C have parent that is B. And then I'll try union C, B. Well, first to do the union, we start with find. So find C, that takes us up to B. Find D, that takes us up to B. And then we need to say which one of these is lighter, which one has fewer nodes. Well, D has fewer nodes. So we're going to make D now point. And that's how we kind of got with this tree. This is kind of like hopefully the best case that we can get. So now the question is, if I have this kind of nice structure where I always make these lighter trees the roots, or sorry, the children, does this actually improve our runtime? So union's runtime is still going to be dependent on find's runtime. So which is going to be a function of the tree's height. The question is, if I'm doing this weighted quick union, always putting the lighter trees down below, what is the worst case height for this tree? So let's try to draw out some examples. So what I'm going to do here on these slides is I'm going to draw out a bunch of these up trees that are the result of unioning them together. On the right-hand side, I'm going to store a little table to help us keep track of the pattern. The table is going to keep track of N, how many nodes are currently in our data structure, and H being what's the height of the tree. So I start with one node and it will have height 0. Okay, not too bad. Now I want to add some more nodes. So what I'm going to do is I'm just going to union two of the sets. I say, 0 and 1. Well, they're both the same, so 1 can maybe go underneath 0. Now when I have two nodes, they're going to have height. Okay, what about next? Instead of going to like 3, I'm going to just kind of skip ahead and double the number of nodes. Now, if I have these two, I want to union them together. Which one goes where? Well, they both have the same weight. So we just choose one to stick underneath the other. So maybe 2 will become the child of 0. Now, the height of this is 2. Okay, let's try that again. We'll double the number of nodes and we'll union those together. Well, they both have the same weight. So we go ahead and just choose one to be the child of the other. Doesn't matter which one you choose, they have the same numbers in them. And we just keep doing this over and over again. So each time I double the number of nodes, I'm going to increase the height by 1, which you might remember whenever you have this kind of, it takes twice as much in order to increase something by 1, that's kind of our logarithmic behavior. So if we use this weighted quick union, we're going to have log n height, which then is just so nice when it comes to any of these find operations or union operations, is we have this logarithmic behavior, which is exactly kind of a really nice kind of runtime to have. You know, it's better than O of n. It's not quite constant time, but it's definitely better than O of n. So you might be wondering, why are we using the weights, the number of nodes, rather than the heights? And we use the number of items in a tree to decide which root we're going to use. We don't want to, we could use the height if we did some kind of like heighted quick union. Asymptotically, it would end up having the same height. But it's a lot easier to track the weights, just the number of nodes, because you don't have any of this complex logic of, does this operation change the height of the tree or does it not? So it tends to be that this weighted quick union is a bit easier to implement. Even though it can run into some weird edge cases, you'll still have this kind of log height. Now, this weighted quick union runtime now kind of gets us kind of the best of both worlds. We get this logarithmic find, we get the logarithmic union in the general case, and in the special case, I added a new row here. In the special case that we're just unioning two roots, we still get that constant time. So this is pretty darn good. But there's going to be one final optimization we're going to make, which we're going to pick up next time, which is the idea of path compression. At the very simplest, you can kind of ignore this for now, we'll pick it up again, is whenever you're doing a find operation, since you already have to start at a node and go all the way up, you might as well, while you're there, update it and compress the tree so that future calls to find will be faster. Don't worry about that quite yet. The most important is to understand quick find, quick union, and this weighted quick union. We'll talk about path compression next time.